prior to this point, what we've talked about is, given this unknown pathogen, how do I reconstruct its genome sequence from just the short reads? That was week 2. Then we talked about how do I annotate this unknown genome sequence that I've reconstructed? That was week 3's topic. And then we fast forwarded toward the middle of the pandemic where we were like, okay, well, what if I already have this high confidence reference genome that I can compare against? Oh, you got microphone muted on this device and setting somewhere. Oh, no worries. Yeah, you can just type in the chat then. That's totally fine. But yeah, so then week 4, we were thinking, well, hold up. Now that I have this high confidence reference genome, I don't have to assemble these new genomes that I collect from scratch. I can maybe compare them against this high confidence reference genome that I already have. They're going to differ from it a little bit, but not too much. They're going to be very similar to it. So then that kind of helps us speed up and improve the accuracy of subsequent genome sequences that we collect kind of like in the middle of the pandemic. And that's really what we're doing at UCSD as part of the Return to Learn project. But then kind of we ended week 4 by saying, okay, now I know how to collect all of these different viral genome sequences from all of these different people. What about those epidemiology questions I asked back in week 1? That was kind of our focus. So today we're going to talk, so on week 5, we mentioned how do we compare multiple genome sequences that we collect, and we called that multiple sequence alignment, basically lining up the different genome sequences that we collected to kind of detect homology, detect like what letters correspond to each other in those genome sequences. And I kind of hand wavy said, hey, this is important for doing downstream evolutionary studies. And today we're actually going to talk about that. So today the topic is inferring a viral phylogeny. So basically input is that multiple sequence alignment that we constructed, and output is the evolutionary history of the virus. So here's a general outline for today. We're going to kind of refresh how we were imagining mutations happening along a phylogeny, so along an evolutionary tree. And then we're going to get into a little bit of like math heavy-ish stuff by introducing what are called continuous time Markov chains and kind of going over some of the models of nucleotide evolution. And then we're going to end by talking about what approaches we can take to use these models of evolution that we come up with to infer an evolutionary history from that multiple sequence alignment. So first, I'm going to go to the beginning. So mutations along a phylogeny. This is kind of a refresher from back in week 1 or so. But remember that if I have this evolutionary history and I have this ancestral genome sequence, I can imagine evolution as just kind of being mutations occurring as we go forward in time. Remember, down the tree is forward in time. So like maybe along this branch, this G turned into a C. Along this branch, maybe this G got deleted. And any mutations that happen get inherited all the way down. And then remember, we mentioned that we don't get to see that evolutionary history. And in reality, we don't actually get to see these gaps either. What we observe are just these genome sequences. So last week, with multiple sequence alignment, we've kind of solved that first problem. We figured out how do we stick those gaps back into those sequences, right? That was the whole purpose of multiple sequence alignment, was determining where do these gap spaces kind of fit. So now today's goal is how can we use this multiple sequence alignment to kind of go backwards, to predict what is the most likely evolutionary history of these sequences. Okay, so any questions so far before we jump forward? Kind of make sense? Okay. Cool, so, makes sense, nice. So continuous time Markov chain. So first I want to introduce the concept of a Markov chain. And these are kind of advanced statistical features. So you're gonna maybe learn about them later in an upper division course, but just kind of a brief intro to what it is. A Markov chain is what's called a weighted graph. So it's a network, so graph means network. And the links between the nodes in the graph, the links between the nodes in that network have weights. They have some numeric value associated with them. And specifically, the nodes in this network represent states. So they represent states that I could exist in. And the edges represent transitions between states. So going from one state to another. And the edge weights represent transition probabilities. So the weight, the numeric value along a given edge, so the numeric value on a given link represents the probability of going from one state to the other. And this sounds really weird, kind of hypothetically, but I think this example might help exemplify it. So we could theoretically represent weather as a Markov chain. So the nodes represent states, and in this weather example, the states are what is the weather in San Diego. So the weather could be sunny, cloudy, or rainy in this simple example. The edges represent transitions between states. So given that today is sunny, this edge represents the transition of tomorrow being cloudy, right? Given that today is cloudy, this transition represents the transition for tomorrow to also be cloudy, right? So basically from one day to the next, these edges, these links represent the transition from one state to another state in the next day. And then the edge weights represent transition probabilities. So like if today is sunny, transitioning from today being sunny to tomorrow also being sunny has maybe 70% probability versus today being sunny, but then transitioning to tomorrow being cloudy maybe has 20% probability. And today being sunny, but then transitioning to tomorrow being rainy maybe has 10%, 0.1 probability. So we can kind of represent reality or like the states of some real thing that changes using this Markov chain. Any questions about this example or kind of any questions about what this Markov chain means? Kind of makes sense? Okay, all good, nice. So the term Markov actually has an important property associated with it. So the Markov property basically is dictating that Markov chains are memoryless. Memoryless is a fancy term that we're going to define in a second. Basically, memoryless in super mathy terms, it means that the probability that the state that you're in at time I+1, given what states you were in every single time period in the past, equals the probability that you're in state I+1, state X at I+1, given what state you are at time I. And this is super math, hand wavy, don't worry about it. Just in English simple terms, what this means is that where you go next only depends on where you currently are. So in my weather example, we're kind of simplifying our assumption by saying the probability that tomorrow is cloudy only depends on the fact that today is sunny. It doesn't matter what the weather was like yesterday or the day before or the day before that. It's memoryless. I don't care about any of the states in the past. Basically, the probability of where I go next only depends on where I currently am. Does that kind of make sense? And then in a later class, you might deal with this probability definition a little bit more. But for now, I think this English definition is good enough. Okay. So how do we define a Markov chain? Well, first, I have to figure out what the states are. So in my simple weather example, the states were sunny, cloudy, and rainy. And then I have to define what are the initial state probabilities. So at the beginning of whatever process I'm hopefully trying to model, what is the probability that I start in any of those given states? So in my weather example, maybe I'll say that the initial probability of starting, like the probability that the very first day that I look at happens to be sunny is 70%. The probability that the first state that I look at happens to be cloudy is 20%, and the probability that the first state is rainy is maybe 10%. So just what is the probability that at the first time period I'm in any of those given states? Okay, and then we have to define the transition matrix. So we have to define what is the probability of going from any of our states to any of our states. So those edges that I represented on that visual depiction of the Markov chain, I can kind of represent in this table, in this matrix, where the rows represent where I'm coming from, and the columns represent where I'm going to. So for example, the probability of going from sunny to sunny is maybe 70%, from sunny to cloudy is 20%, from sunny to rainy is 10%, etc. Okay. So what's a big problem with this model of weather that I said? Maybe, does anyone have any, like, do you want to poke any holes at it? So I mentioned that basically the probability that today is sunny and then tomorrow is cloudy, basically each day has its own fixed weather. Is that realistic, or what's up with that? Any thoughts? So is it like a safe assumption to think that, oh, so someone said, yeah, so one day can have several weathers. Exactly. So the problem with this model that I'm showing you is that I'm modeling weather as being a discrete event. I'm modeling it as being one day is one weather, the next day is a different weather, or maybe the same, but like basically each day has a weather. But really, weather is continuous, right? If it's sunny right now, maybe it's sunny, but then slowly the clouds come in, and then slowly the clouds leave and it becomes sunny again, or maybe slowly the clouds come in, then it starts raining, then it stops raining, then the clouds leave, right? So treating weather as this like discrete, every day is one type of weather, this is way too strict. There's a question, are we assuming that it's pseudo-random or actually random? In general, we should assume that it's actually random according to these probabilities. Yeah, that's a great question. So yeah, we're assuming true randomness here. But yeah, so this discrete property is problematic here. So we can actually expand on Markov chains by introducing what's called a continuous time Markov chain. So in the previous example, time was discrete. So time had individual distinct steps. We had day steps in the previous example, but maybe your steps are, whatever metric of time step you want to use. We were using discrete time steps in the previous example, but in reality, weather and many things that we want to model are continuous time. So a continuous time Markov chain is just literally, we take a Markov chain, but instead of treating time as being discrete, we treat time as continuous. So time progresses continuously instead of discretely. And instead of having transition probabilities, right? A probability is like the probability of like flipping a coin and then something happens. But we don't have these discrete coin flips anymore. We have these kind of smooth transitions between states, but some transitions are faster than other transitions. So like transitioning from like sunny to cloudy is going to be faster than transitioning from sunny to rainy directly. So instead of probabilities, we have rates. But the concept is all still the same. And I don't want to get too much into the nitty-gritty of continuous time Markov chains because they get like pretty complicated pretty fast. But just imagine that we kind of take those discrete time steps, a day, maybe I shorten it to an hour. I shorten it to a minute. I shorten it to a second. I shorten it to a millisecond, a nanosecond. As we kind of infinitely shorten the time between steps, that is what a continuous time Markov chain becomes. Or that's what a discrete Markov chain turns into a continuous time Markov chain. Does that kind of make sense? Ish. Yeah, nice. Okay. So why did I go on that long detour about modeling weather? Well, it turns out we can use continuous time Markov chains to model the evolution of nucleotides. So we can model nucleotide evolution using a continuous time Markov chain. And kind of going back to what I mentioned, how do we define a Markov chain? Well, we have to define the states, the initial state probabilities, and the transition rates in this case. Instead of probabilities, they're transition rates. But yeah, so the states here are just ACGT, right? The states are what nucleotide am I currently? And then the initial state probabilities, this just kind of depends on the specific model of evolution that we're using. I'm going to talk about this in a little bit. And then the transition rates also depend on the specific model, but they're basically describing, given that I'm currently so for each position of my genome, I kind of treat each position as evolving, mutating on its own. And let's say that the first position of my genome is currently an A. this row of the transition matrix represents what is the rate that it stays an A in the future versus it transitions to a C, which would be a substitution, or it transitions to a G, or it transitions to a T, which would, all those would also be substitutions. So we're kind of, instead of whether, it's basically ACGT as 4 states that I can transition between for this specific nucleotide in my genome. Okay, and for simplicity, a lot of the models of nucleotide evolution are what are called time-reversible. So basically the transition rate from going from one state to another is the same as the reverse transition rate. So the transition rate of going from some letter X to some letter Y is the same as the rate of going from some letter Y to some letter X. So like the rate from A to C is equal to the rate from C to A. This is just a simplifying assumption that we typically make. And because we're making this simplifying assumption, this bottom half of our transition matrix doesn't actually really matter because it's kind of strictly defined by the upper half. If I can define these 6 rates of transition, then I can reconstruct what all these other rates are because they strictly depend on those rates. And if that's kind of confusing, just think about probabilities, right? When I was dealing with discrete Markov chain, I had probability of going from A to A, probability of going from A to C, A to G, A to T. If you told me the probability of A to C, A to G, and A to T, the probability of A to A must be 1 minus the sums of those probabilities. So we could do a similar thing with rates. I don't want to get into the nitty-gritty details, but just know that we can reconstruct all of these other ones if we only define these properties. Does that kind of make sense? And when you get to like genetics classes and stuff, you're going to learn about degrees of freedom. So this model has 6 degrees of freedom. There's 6 parameters I can change, and then everything else kind of strictly depends on those. Okay, cool. So basically, so now I'm just going to kind of go through a few different models of nucleotide evolution. These are also all on Wikipedia. I don't want to get into the nitty-gritty of any of them. I just kind of want to show how modeling evolution has evolved over time and kind of how simple versus how complicated can these models potentially get. But the key takeaway of this next really long kind of rapid fire round of different models that I'm going to go on is just the fact that I want you to highlight like where they can differ and kind of where can we make simplifying versus more complicated decisions. So the very simplest model of nucleotide evolution is called the Jukes-Cantor 69 model, which was created by Jukes and Cantor back in 1969. And this model is the absolute simplest model of evolution. It assumes all of the nucleotide frequencies are the same. So the probability of having an A versus C versus G versus T, they're all equal, they're 1/4. And it assumes that the transition rates are all equal. So it assumes that it's like an A mutating into a C versus a C mutating into an A versus an A mutating into a G, G to A, A to T, C to G, right? It assumes all of these possible mutations are completely equally likely. So basically, as long as so this model only has one free parameter, it has just one transition rate, that all of those 6 transition rates that I describe are all just equal to that single rate that I define. So it just kind of treats all mutations as being identical. Okay, does that model kind of make sense? And I think what's important is, especially when you get to like a genetics or a molecular biology class, this is actually pretty unrealistic. And you're going to learn more about the biochemistry behind DNA in the future, or I guess in the case of viruses, RNA. But you're going to learn about the biology between them in the future. But it turns out that it's actually unrealistic to assume that these are all the same. So then in 1980, a researcher named Kimura came up with a different model, which we call the K80 model, Kimura in 1980, that just like the JC69 model, it's making this simple assumption that maybe all the probabilities of the nucleotides are equal, but it distinguishes between the two following events. And these you're going to probably learn more about in a genetics or a molecular biology class, like maybe BICD 100 or BIM 100. But basically, in DNA, there's what are called transitions. So each of the nucleotides can either be classified as a purine or a pyrimidine. So purines are A and G, pyrimidines are C and T, and mutations that go from purine to purine or pyrimidine to pyrimidine, these are known as transition mutations. And transversion mutations are the ones that go from purine to pyrimidine or pyrimidine to purine. So transitions are A to G or vice versa, or C to T or vice versa. And then transversions are everything else. And for reasons that you're going to learn about later in a biology class, biochemically, these two phenomena are different. And it's easier to transition within your own kind of class of nucleotide than it is to transverse across them. So this model makes it slightly more complicated, where it says, okay, I'm going to actually have two different rates of transition, one for these, one for these. Okay, so we're slightly getting more complicated. Then in 1981, Kimura made another model, still making this like this equal frequencies assumption. But now he's saying, well, actually, let me split even further. Let me say that there's those same A to G and C to T transitions that I have, but let's split up the transversions into these other kind of categories that take into account some of the more metabolic biochemistry properties, or maybe not metabolic. They take into account some of the more biochemical properties between those different types of transversions. So it's just kind of become even more specific. It's like making it a little bit more complicated. Okay. Then also in 1981, there's a researcher called Felsenstein who basically, he took the JC69 transition rate, so assuming all mutations are equal, but all of the base like all the models that we've talked about so far, the base frequencies were all equal. So the probability of A versus C versus G versus T were all 25%, right? 1/4 in all of the previous models. But in this model, he's reverting back to this simple transition rate where all the transition rates are the same, but he's allowing these base frequencies to vary. So the 4 base frequencies, so probability of A versus C versus G versus T, can actually all be different in this model. And then in 1985, these three folks kind of mixed together the K80 model with Felsenstein's model. So they took the K80 transition rates and they took the F81 different base probabilities and kind of like made a model that allows both of those properties to hold. And then in 1992, this model came out where kind of you force A to match T and you force C to match G. And this is kind of inspired by the fact that, like, you know, A pairs with T, C pairs with G in the actual DNA strands. So maybe we would expect these to match. And then in 1993, we had an even more complicated model called the TN93 model, where you allow all 4 of the probabilities to change, and you allow these types of kind of mutation rates to exist. So this is how they look like in the matrix. And then the last model that I want to talk about is called the general time-reversible model, which was proposed in 1986, which this is the most generalized model that we can use. Basically, we're allowing all 4 of those probabilities to change, and we're allowing all of those 6 rates to change. So we're allowing different probabilities and different rates. This is the most general out of everything that we've talked about. Okay, so I threw a lot of information at you. Not all of it is necessarily important to memorize. I think the main takeaway is just GTR model is the most flexible of all the models that we've talked about. We could technically instantiate it via any of those other models. But the main thing is just there exist all these different models and they all make different simplifying assumptions. Any questions so far? Maybe? Kind of makes sense-ish. Okay. Okay, so why did I go over all of those random sounding models? What was the point? So let's go back to phylogenetic inference. Our goal for today was we had this multiple sequence alignment that we were able to reconstruct using those techniques we talked about last week. And I want to use that multiple sequence alignment to try to infer what the evolutionary history might have looked like. So first, I'm going to try to answer a different question. So instead of just asking the question, how do I go from multiple sequence alignment to a tree? I'm going to answer a slightly different question. I'm going to answer the question, given a candidate tree, how do I compute the score of that tree? So given like my multiple sequence alignment and given one possible tree that maybe explains the evolutionary history, how do I score it? How do I determine how good this tree is at describing the evolutionary history of this multiple sequence alignment? And let's think about what tools I have at my disposal to do this score. Well, I have one of those models of nucleotide evolution. So I went on that long tangent of listing all of those different models of evolution. Let's assume that I have a parameterized model of nucleotide evolution. So let's say GTR model or whatever model out of those that I pick. Let's assume that I know what model I'm using and what the different parameters of that model actually are. I have my multiple sequence alignment, which I was able to construct using the techniques from last week. And I have this candidate tree that I'm trying to score, this hypothetical tree that I want to see, is it good or is it bad? So it turns out that there's an algorithm that lets us compute the probability of observing this multiple sequence alignment given this tree and this model of evolution. And this algorithm, it's called Felsenstein's tree pruning algorithm. Felsenstein was one of those researchers I mentioned in that long list of models. And basically, so I don't want to get into the nitty gritty of how this algorithm works, but just trust me that there exists a very efficient algorithm where if you gave me a multiple sequence alignment, you gave me a tree, and you gave me a model of evolution, I can compute the probability of observing that multiple sequence alignment given the tree and that model. Okay, does that kind of make sense what I'm saying here? So given the models, given a multiple sequence alignment, given a tree, there exists an approach for computing the probability of observing that sequence alignment from those. Nice, yeah, sounds cool, awesome. So what does this help us do? Basically, I can use this probability as a score. If you gave me one tree, I can compute this probability. If you gave me a different tree, I can compute its probability, and then whichever one of those two has the higher probability, I'm going to treat that like a score. And I'll say that the one that has the higher probability is the better one. So what this helps us do is if you gave me a tree, this helps me compute the score of that tree. But how does this help me find a tree? Remember, I don't have a tree in the first place. I just have the sequences. How does this help me construct a tree from those sequences? And that I want to introduce a technique called maximum likelihood phylogenetic inference. This sounds scary, but let's break it down. Phylogenetic inference, that's what we're talking about. We're inferring a phylogeny. We're inferring an evolutionary history. And maximum likelihood means I want to maximize some likelihood score. So how does this look like? Well, first I can compute some simple, quick and dirty tree. So there's an algorithm called neighbor joining that basically uses pairwise distances to hierarchically merge pairs of individuals kind of over and over and over again and build a tree structure. So neighbor joining, it's not going to give me a good evolutionary tree, but it's a nice, simple, and kind of quick and dirty algorithm to just get a tree. So given sequences, I can compute a neighbor joining tree just by running this neighbor joining algorithm. And that gives me some tree. And then given that neighbor joining tree, I can compute a likelihood score from this tree using that probability that I just described. So probability of observing my multiple sequence alignment given this neighbor joining tree and given my model of evolution. And then what I could do is take an iterative approach to doing a tree search. What I could do is basically make a small modification to the current tree. So maybe I'll rip off one of the branches and kind of stick it on somewhere else. This is called tree grafting. I'll just kind of like rip off a part and stick it somewhere else. So make a small modification to the tree, then compute the likelihood score of that new tree. And then if that new tree has a better score than the previous tree, I'll keep the new tree. Otherwise, I'll keep the original tree, right? So basically, I kind of like modify my tree, compute the updated score, and then see if my score got better, I'm just going to keep that new one as my new better tree. I can keep repeating this process, rip off a branch, stick it somewhere else, compute the likelihood. Rip off a branch, stick it somewhere else, compute the likelihood. Keep doing this over and over and over again while the likelihood score, while this probability that I can compute keeps increasing. And then eventually it's going to converge at some point. That likelihood score is going to maybe increase a little bit, increase a little less, increase a little less, increase a little less. Eventually it's going to converge to some maximum likelihood. That likelihood score is going to hit its maximum. And whatever tree I get that has that maximum likelihood score, I call that my maximum likelihood tree. Does that approach kind of make sense? Basically, I have a score, I make a quick and dirty tree, and I keep modifying it until I converge on a better tree. Okay, so what is the computational complexity of this? So the phylogenetic inference problem, so given a multiple sequence alignment, how do I infer the absolute best evolutionary tree? This problem is what's called NP-hard, and you're going to learn about what that means if you take a future computer science class. But for our purposes, what this means is that no efficient exact solutions exist. So basically, to come up with the truly optimal tree, like we can prove that the computational problem of finding the optimal tree is way, 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 way too slow. There cannot exist fast solutions. Just like with multiple sequence alignment, how I mentioned multiple sequence alignment was big O of k to the n. So multiple sequence alignment, the optimal algorithm scales exponentially with the number of sequences. And I mentioned last week that we don't want exponential growth. So people use heuristics to try to speed up that algorithm. So just like with multiple sequence alignment, same thing goes here. People use heuristics to hopefully speed up this phylogenetic inference step. So let's say that n equals the number of sequences, right? So one sequence per person. K is the length of each sequence. And then let's say A is the size of the alphabet. So for DNA, A is just ACGT. So the best heuristics are big O of n to the 1.5 times log n times Ka in time complexity. And then, so here's like some fancy schmancy numbers, but kind of the key takeaway as far as you're concerned is that basically these techniques scale almost quadratically with respect to the number of sequences. So this is very similar to multiple sequence alignment, where basically these heuristics, if I double the number of sequences, I'm going to roughly quadruple the time it takes to estimate a tree. Okay, so these heuristics, they're decently fast. And as we've been talking about all course, we don't want to reinvent the wheel. So here's a list of some current state-of-the-art inference tools. One of them is called IQ-Tree. This is kind of the most popular tool for doing maximum likelihood phylogenetic inference. And it's typically the best trade-off between accuracy and speed. And usually in a lot of computer science applications, you're going to have that trade-off that you're going to have to make, where maybe the more accurate algorithm is slower or the faster algorithm is less accurate. So that's typically the trade-off that you're going to make. And here, this is kind of the best trade-off between accuracy and speed that exists so far. I have links in the slides if you want to take a look at the code base. It's a really sophisticated tool and it's like super awesome. So yeah, definitely I recommend taking a peek under the hood. The fastest tool, but which is generally lower accuracy than the others, is a tool called FastTree2. And you can find the source code as well as a description of how it works on its website. And then the slowest tool, but generally the most accurate, is a tool called RaxML-NG. And you can find the tool's website here, and kind of the source code is here. So at UCSD, we typically use IQ-Tree or FastTree just because COVID-19 is so large in terms of data set size that, these are the only ones that really scale to the size that we need.